Species distribution modeling is a powerful application of GIS that combines species occurrence data with environmental variables to predict the geographic areas where species might be found. It is essentially a way to map out potential habitats or ecological niches for species based on their unique environmental and climate preferences. The two main types of GIS data used in species distribution models are species occurrence data, which usually consist of point locations where a species has been observed or confirmed to be absent, and environmental variables, which are the spatial data layers representing factors like climate, topography, land cover, soil types, or hydrological features. These variables are often obtained from remotely sensed imagery, interpolated weather stations, and digital elevation models. Species distribution models are similar to habitat suitability models in that the aim of both is to understand where good habitat exists for species, but they do this in very different ways. While suitability models use overlay techniques to identify habitat, species distribution models use statistical or machine learning algorithms to model the probability that a species might be found in a particular location. With suitability models, there is no need for actual locations of species, but these data are a critical input for species distribution modeling. When constructing species distribution models, it is common to only have observations of species presence. This is because species absence data is much harder to obtain. Think about it. If you don't see a species at a particular location, do you really know whether that was because the species cannot survive there or simply because you failed to be there at the right time or in the right conditions to observe that species? Because absence data for ecological observations are so difficult to obtain, most species distribution models are built with what is called presence-only data, meaning we only have data on species presence, not species absence. That limits the types of models that can be used for this purpose. The lack of absence data calls for specific types of modeling that can handle these cases. One of the most common forms of presence-only modeling is called MaxEnt, which is an abbreviation that stands for the maximum entropy approach. MaxEnt is a machine learning model, meaning that the model aims to learn where a species might be found in a study area based on training data that are provided by the user. These training data come from known locations where a species was observed, as well as a set of environmental variables that describe the site conditions. The environmental variables can either be continuous, like elevation, or they can be categorical, like land cover. The model uses points sampled from the background to get a sense of the baseline conditions in the study area. The model then estimates the probability that a species would be present in a given area by maximizing the entropy of the model. Essentially, it finds the most likely distribution of a species given what is known from the training data about its habitat preferences and the environment in which it is found. The output map from a species distribution model is a map of predicted probabilities that range from 0 to 1, where 0 is a lower likelihood that the species would be found, and 1 is a higher likelihood. Model outputs also typically include response curves that show how the species might respond to each individual environmental variable. MaxEnt is just one of several kinds of models that can be used with presence-only data. Other types of models that are frequently employed for presence-only species distribution modeling are random forest, support vector machines, and generalized additive models. Each of these models works in different ways with the data provided to make predictions. Therefore, the outputs are likely to vary from model to model. Accuracy metrics like the area under the receiver operating curve, or AUC, can be used to understand how well the model fit the data and compare different models. Other times, researchers will ensemble the outputs of multiple models together to capture this variability in a single map. The benefit of ensembling models is that it is also possible to produce a map of the uncertainty in predictions, with areas of higher uncertainty where the models diverged in their predictions, and areas of lower uncertainty where the models made similar predictions. These approaches are useful if the outputs are to be used for decision making so that the full power of the models can be communicated. To summarize, species distribution models are a valuable tool for mapping where species might be found in the environment, but it is important to understand the limitations of the data that go into the model and any uncertainty in the models themselves when using the prediction results for decision making.